Yeah, so all thermodynamic processes using this apparatus must satisfy the first law of thermodynamics, which states that the heat absorbed during the process must be equal to the change in the internal energy of the enclosed gas plus the work done by the gas on the piston. Well, since the fundamental variables are the volume V and the pressure P, processes are described by curves in the VP plane. Now, such curves could be represented by vector-valued functions with this parametric representation in terms of the parameter t. Now, the parameterization can always be chosen so that the parameter t runs from some value big T to t plus 1 during the process. And using this notation, the work done by the enclosed gas on the piston is given by the integral of the product of the pressure and the derivative of the volume with respect to the parameter t. So, and generally, all parts of the apparatus will conduct heat to some extent, but thermodynamics uses two limiting processes called isothermal and adiabatic, which we now discuss. So let's move down here a bit. So in an isothermal process, the internal energy remains constant, and so the pressure and temperature at some point on this curve must satisfy this equation, where V0 and P0 are the initial. So we've taken capital T to be 0. The result of setting this equal to 0 and solving for P of t, we can get that. And we can plot that curve if we take, as the volume extends from Vt equals 1 to Vt equals 2 using this. So we take the pressure using the expression or the equation above, and then set the values in and then plot the curve. So this is what it looks like, and we see that the pressure drops from its value 1 to a value 1/2 as the thing expands. And now we calculate the work using this equation, where C is some constant. So the work done performed in the isothermal expansion, that's the work by the gas on the piston, is equal to this. So we'll remember that relation. An adiabatic process, in it no heat enters or leaves the system, so that in any change of the volume of the enclosed gas, the first law requires that the sum of the change in the internal energy of the enclosed gas and the work done by it on the surroundings must be 0. Thus, if the gas is expanding, the work done by the enclosed gas is positive, so that its internal energy will be reduced. And this occurs because if the piston is moving away from the gas in each collision of an atom with it, on reflection in a collision with the piston, its component of velocity along the axis of the cylinder will be reduced by twice the velocity of the piston. And the rate at which heat enters the system, which is 0, is thus the sum of the rate of change of the internal energy plus the rate at which the piston does work, leading to an equation which we can derive using that. So it's it's 3/2 times the volume times the derivative of the pressure and plus 5/2. Now, if we divide this equation by the internal energy, the result can be seen using this. And what we can see is that the first term is the derivative of the pressure divided by the pressure, and the second term is 5/3 the derivative of the velocity of the volume divided by the volume. And we can see this is perfect derivative.
It's a perfect derivative.
Yes, which can be, and we can find this by integrating using this. And to find the, in this case, we'll take the origin of the parameter t to be 1, so that an equation for the constant can be obtained by setting t equals 1 in that. And then can be inserted with the integral and the result set equal to 0 and solve for p of t using this. And what we find is that the pressure is equal to P1 times the 5/3 power of the volume at the start of the process, and then divided by this. In other words, this quantity P1 or PV to the 5/3 is a constant in an adiabatic process. So let's see what the final pressure is. So we I think we got that wrong. So I think we needed that to be A. No, sorry. The initial pressure is the final pressure in the isothermal process. We're going to, and then this expression here is called the adiabatic equation of state, and it can be visualized in the case where the final volume is 3.
Yeah.
So let's do that here. So that's what it looks like. So the pressure falls from 1/2 down to a much lower value. And now let's visualize the two processes together. So this is the red curve is the isothermal expansion, and the blue curve is the adiabatic expansion. And we can plot the internal energy of the enclosed gas during the adiabatic expansion, and it looks something like that. Right, so now we're ready to complete the story and look at the ideal gas Carnot cycle. So we've described the first two processes in the Carnot cycle, an adiabatic expansion.
And what we're looking for now, with a few words, can you say, is to...
Yeah, what we're going to do now is we've done is we've now done an isothermal expansion followed by an adiabatic expansion. And in that process, the internal energy of the gas has gone down, as we see here. And now what we're going to do is we're going to do an isothermal compression in this lower energy state, followed by a adiabatic compression back to the original state.
Yeah.
And that's called the ideal gas Carnot cycle.
Mm.
But we can't choose all those arbitrarily, as the following calculation shows. So we suppose that if we do that, the 4 state points are P0, V0, the initial one, the state after the isothermal expansion, and then the state after the adiabatic expansion, and then there'll be a state at the end of the isothermal compression, and which is this one here. And then we'll go back to the original state. So our first equation is the one for the isothermal expansion, which is that one there. And then the second equation is this adiabatic equation of state, which says that PV to the 5/3 is a constant. So we equate those. And then the third equation is an isothermal one, so this says that the internal energy at the end of the isothermal compression must be equal to the internal energy at the end of the adiabatic expansion. And then finally, our fourth equation is that the P0 V0 to the 5/3 this is in the adiabatic compression, is equal to the value at the end of the isothermal compression. Well, we've got 4 equations and we've got 8 unknowns. So what we can do, we can express 4 variables in terms of the other 4. And it's up to us to choose the variables we assume known in some sensible way. Well, for the variables assumed known, we choose P0, V0. In other words, we need to know what the initial state is. We need to know the volume of the system after the isothermal expansion, and we need to know the volume after the adiabatic expansion, and then we should be able to solve for all the others. Well, we can do that using Mathematica. So the remaining variables are P1, P2, P3 and V3. So let's see if Mathematica can handle that. And we find 2 solutions, of which the second set is the appropriate one, since everything has to be positive.
Yes.
Okay, so that's the relevant one. And we'll leave you as an exercise to solve those equations manually one by one. So have fun.